So yeah, thanks a lot for the kind invitation and for the introduction also. So as you said, I'm going to talk about deep learning in jet modification, deep learning jet modifications in heavy ion collisions. Let's see if this works. So a bit of a perhaps unnecessary gentle introduction. There's a new phase of matter that should appear at very high temperatures out from normal matter, where color is confined and hadrons can be scattered. This new phase, which we call the quark-gluon plasma, should have filled the universe microseconds after the Big Bang. And it should behave pretty much like a gas due to asymptotic freedom at really high temperatures. However, close to the phase transition, we do wonder which are the properties of this system. These heavy ion collisions are the little bangs, and we can reproduce this state of matter in ultra-relativistic heavy ion collisions. As the equation of state measured from lattice QCD presents, there's a rapid crossover transition above the pseudo-critical temperature. The confined matter can reveal itself as a rapid increase in the number of degrees of freedom above this temperature. And these asymptotically approaches the non-interacting limit. So with RIC and LHC, these heavy ion collisions, what we are doing is exploring parts of this, so to say, phase diagram, and where what is seen is that there are very strong collective effects in which thousands of particles are correlated according to the initial geometry, and it resembles pretty much an hydrodynamic explosion. QGP has been also labeled the most perfect fluid. If you have hydrodynamics, you expect that spatial anisotropies should translate into pressure gradients. There's even some special events in which you can see it literally by eye, how these anisotropies translate into pressure gradients through the particle distributions. Relations of preferred directions are quantified in the experiment through the so-called flow coefficients. V2, V3, V4 respond to different geometries of the related to the collision and its fluctuations, elliptical, triangular, quadrangular, and so on. The hydrodynamic simulations, they do point to the presence of an almost ideal fluid by comparing data with hydrodynamic models. And it's interesting to note that this value of the shear viscosity over entropy density, it pretty much resembles the one you would get from a fluid without quasi-particles, or with a fluid at least that is very strongly coupled. These limit obtained in the gauge string duality that in principle could still, there's no reason why it should not apply to QCD in particular, although the conformal of QCD hasn't actually been found. Seems to be preferred by data, perhaps indicating that this is a system that lacks quasi-particles and that it is very strongly coupled. So how can we probe this very interesting system? There's no such thing as a fixed target experiment. So because this is a system that has a very short lifetime, so what we do have are jets that are produced in the collision itself. These very schematic, you have some incoming partons from the nucleons that belong to the nucleus that undergo a hard scattering. They have a steeply falling spectrum, so high PT production becomes increasingly rare. They are back-to-back in transverse plane, but not back-to-back in rapidity because it's a hadronic collision. These highly virtual partons will split according to the Diglap evolution, and they form a collimated structure due to the soft and collinear divergences of QCD, and also because of the angular ordering of the soft stuff emitted due to color coherence. Jets are defined through a clustering algorithm and a reconstruction radius R, which is a procedure performed over a set of do not know about what you mean by jet before you do apply such procedure. In proton-proton collisions, you see that this back-to-back jet, pretty clear, with an underlying event that does not present, does not hide the presence of the structure of the jet, even though it has to be properly taken care of. But in the medium, essentially, the main mechanism that occupies us today is parton energy loss. If you have a high energy parton, quark-gluon in the QGP, from a perturbative QCD point of view, it will emit quanta, which in turn can emit more quanta, developing a cascade that should eventually hydrodynamize if we assume that the QGP does behave as a hydrodynamic system for some part of its evolution. Here is a schematic representation of the one-gluon distribution that it is modified due to splittings and also due to scatterings that broaden the system. This turbulent cascade features a sink at the energy of the order of the temperature, the scale of the medium. And one still needs to figure out precisely which is the necessary length that one needs to reach this turbulent regime. But there is ongoing work such that we will have an answer to this pretty soon. Hydrodynamization from the point of view of a turbulent cascade in a realistic system. From non-perturbative Superior-Mills, high energy partons in the QGP are dual to strings that fall into a black hole and hydrodynamize. You have this schematic picture here of a string whose endpoint is initially has all the energy along the boundary, which is the real world dimensions. And as it propagates in the presence of a black hole, that is the dual of the plasma, it gets pulled down, and pieces of the string that represent the gluon cloud around this energetic quark, in this case, fall into the black hole and hydrodynamize. So thanks to the duality, you can perform these computations at infinite strong coupling, and the perturbed metric on the boundary induced by the string, it determines the modification, the change in the energy momentum stress tensor at the boundary, which includes both the hard and the soft modes. If you take the long wavelength limit of this quantity, you actually get, which is the amount of energy that is being hydrodynamized per unit length, the hydrodynamization rate, which actually exactly corresponds, can be proved, to the pieces of the string that fall into the black hole. So we do have a set of different pictures, which, however, present similar phenomenology, which is like the degradation of the energy of the partons towards softer modes. Here you see a dijet event in a heavy ion collision. So these jets, as they traverse the QGP, they get modified, they get quenched, so they can provide information about the medium properties. As the jets deposit the energy and momentum in the QGP, they can modify the background in their turn. Here you could say that this jet has more energy than the other one, so it's likely that it traverses more QGP. However, this would be true if jets didn't have a substructure. But we know that the traverse length is not the only thing that determines energy loss for a jet. For instance, I'm sure many of you will remember this interesting study using Joule, which is a Monte Carlo jet quenching model that has allowed us to gain crucial insights about the phenomenology of jet quenching. These Monte Carlos, they naturally include the multi-particle nature of jets. Since they use parton showers, whenever they look at the features of jet energy loss, from the notion of having a single particle object that propagates through the medium. It's natural to include these particles because they feature a high energy, high virtuality evolution that is determined from the D-Lab evolution. Here in this study, what they did is study digest asymmetry, having the jets either produced with a realistic sampling position using a Glauber, most likely, versus the digest asymmetry that would obtain if you put a digest sample exactly at the center of the collision, meaning that both leading and subleading jet, both jets have to traverse the same length. And what they found is that in this model, the amount of digest asymmetry was barely affected by the amount of traverse length or by the position by the amount of traverse length. It was rather determined by the mass over the PT of the jet, which is a proxy for the number of vacuum splittings. So it would look from the study that more vacuum splittings would lead to more jet energy loss. Another way in which the jet substructure has allowed us to understand phenomenology is by looking at the jet suppression versus hadron suppression. Here in red, using the hybrid model, you see jet suppression, and in blue, you see hadron suppression. The level of suppression is different precisely because the leading hadrons that contribute the most to this spectrum, they are mostly produced from narrow fragmenting jets. They tend to be the ones that suffer less energy loss. Or in other words, jet is made up of more than a single particle, and therefore it suffers more energy loss. This is connected to the high Z enhancement measured in the jet fragmentation functions. The most natural way to understand both of these features of phenomenology is precisely in the same way that we did with the previous observable, which is realizing that there's a number of the number of vacuum like splittings or the activity of the jet will determine to a large extent the total quenching. Yet another way to look into this phenomenology from this point of view is by looking at the groomed radius between lead-lead jets and PP jets. What one sees with this model, with the hybrid model, is that from the jets that you measure that pass your PT cuts, there's a much more there's an absence of jets that feature a large groomed radius, which would mean like there's an excess of narrow jets over wide jets of the jets that pass your cuts in lead-lead compared to PP. This we understand in exactly the same way we did the two observables before, in the sense that the strong ordering in the groomed radius is because once you have a larger groomed radius, you have a larger phase space for emissions, and you have a larger quenching and therefore a smaller survival rate. So you have a bias towards the narrow jets, and this is actually a very good observable to discuss in more detail. I hope I didn't lose you with all these observables together. I just wanted to show that there's a number of observables that we will be able to understand by using the details that can be extracted with this example, with the groomed radius. So the groomed radius is obtained by looking at all the clustering steps, by declustering a jet and looking at which is the first clustering step in an angular order clustering algorithm that satisfies some kind of hardness requirement, such that a given branch has at least 10% of the total energy of the jet. And what we do typically when we want to measure jet quenching, or we want to determine the amount of jet modification, is to look at these kind of ratios. Measure jets in lead over measure jets in PP. So if you see this absence, meaning the ratio is below 1 of large radius, large groomed radius jets versus the narrow ones, one logical possibility is that the jets in the medium, they do produce emissions with smaller delta R, with smaller groomed radius than in the vacuum. Then this interpretation would presume that the physics is dominated by the medium scale. The medium is producing a smaller groomed radius, replacing the ones that would have happened in the medium. Another interpretation is that jets that that have a larger delta R, which has been defined before which has been defined in the very same event where the quenching takes place, that they are more suppressed and that they don't pass the PT cut of the distribution. And this presumes that the physics governing this observable with these cuts and these samples is dominated by the vacuum scale. So as I already hinted in this model, and as I will try to argue also in real life, this is the appropriate interpretation. This is the most plausible interpretation, and one can understand it in the following way. If you have two jets that have the same energy, they have been defined with the same jet radius R, but have a different fragmentation pattern, it's much more likely that this object, once you put this object as it is already developed in this picture, it will suffer more quenching than this other object. And this is, of course, assuming that most of the energy goes out of the cone. If you have some kind of collinear emissions that broaden the jet, of course, then this wouldn't be true. And that the internal structure is resolved by the QGP, that these splittings have actually been formed and that the medium has been able to resolve it, such that the color dipoles have been decorrelated, or the wavelength of the exchange gluon with the medium is small enough to resolve the separation of this dipole. The scale of the emission, of each emission, as determined by the Diglab distribution, is sampled from a Sudakov distribution in practice for parton showers. And the first emission inside the jet cone, it will determine the available phase space for further in-cone emission. So if you draw a scale T1 with your distribution, it can be a PT scale, angle scale, mass scale for the shower. Then the next scale will be as a maximum one, it will have the previous one. So if you happen to draw a scale T1 prime that is relatively low, you have much less phase space until you reach the confinement scale, where you should resort to hadronization instead of splitting, perturbative splittings, which means that this first splitting is actually a good proxy for the jet activity, for any evolution variable of the ones one typically uses that are equivalent, at least if you include all the appropriate corrections, logarithmic corrections in your parton shower, this will be the case. For instance, you can take lithium.
Sorry, Danny, yeah. Can I have a question? What is this T in your case here?
It doesn't matter. I mean,
but in some cases, shouldn't it be inversely proportional to delta R?
Okay. Yeah. Okay. If it's a formation time, then yeah. Sorry, perhaps I confused you with the T. Yeah.
That's what I thought. Okay. Cool.
Yeah. Thanks for the appreciation. Yeah, you're right. Yeah, formation time would be dominated by the inverse of the mass square.
Right.
Yeah. So you can take PCA8, which is a PT ordered shower with dipole kinematics, and you can take jets that have one groom splitting only, and you will see that the groom radius of the first splitting, in this case the only one, the purple, is very narrow. And if you take those with two, then it's more likely than that the groom radius of the first splitting in the x-axis is wider, and so on. If you have a jet that has a lot of groom splittings in the sense of splittings that satisfy the hardness condition of having at least a 10% of the energy, then it is much more likely that this structure is wider. I mean, this at this point, I hope it has become pretty obvious, and this is even the case for a shower which is not strictly onward ordered, but which, of course, being a QCD jet, it has the features of jet collimation, which preserve the logic that I just explained in the slides before. So there was this recent measurement by Alice about the groom radius that we have just described, and here in the x-axis is the groom radius. You can do this for let over pp, as I just presented, and many of the models, they do share the same feature in which there has been a narrowing. Large groom radius are suppressed, and in particular, if you assume, like in this calculation here, that you only have broadening, you have a single emission that can broaden without considering the quark-gluon fractions. Oh, it's terrible. The battery. Oh, so screwed. Try. I might be able to figure something. Oh, I'm screwed. Yeah, the battery.
Maybe if you stop sharing your video, it would make it last long, right?
I guess you were right all along.
I didn't know.
Turn off the video. All right.
Yeah, we can turn off our video too. Yeah, that makes sense. We'll do that.
And then, yeah, well, perhaps I can reduce the brightness. Then how are you supposed to see the slides again? I have to share with Google Drive.
Yeah, just send the link or something, and then we can pull it up here.
Oh, I'm so sorry.
Speak, I guess. I don't know if that helps or not, but that helps, right?
Yeah. How we can keep going? He has 5% left, and then we're going to lose Danny forever.
We're gonna lose it forever. Yeah, I think if you stop your video, that will help, and keep sharing your slides, right?
Yeah, let's try that.
Yeah, if you stop your video, we stop our video. You keep sharing your slides. I think that will at least get you further. I don't know, but 5% is not very much. So.
I do have 8%.
8%.
Yeah. Well, I guess that's good. Means we will meet the time requirements for sure.
Let's go. I mean, quick talks are good, Danny. Let's go.
Can you see my screen?
Yes.
Okay, so many of these models, they do have this feature. They do have a high energy early shower that is dominated by vacuum-like physics. So one can try to look beyond the bias, as it was done in this recent analysis by Brewer and collaborators. If you just look at which is the modification of the groom radius of the jets that you measure after of the jets that you measure, you will see that they have barely been modified with respect to the initial configuration, to what they had. Essentially, what you're having is a bias towards jets that lost the least energy because of the steeply falling spectrum. If you do the opposite, something that would be similar to having a photon jet selection, then you see if you select jets, you select PP jets and then look for the leadlet jets, no matter what their PT is, above some minimum 10 GB or 20 GB at least, then you will see that these jets actually have a modified room radius due to the physics of energy loss. Otherwise, what you're seeing here, at least in this model, and also in the rest of the Monte Carlos, is essentially the room radius of the jets that pass the cuts, therefore the ones that were barely modified. So this selection bias, we can try to mitigate it using deep learning techniques. We want to know how quench jets really look like. So we're going to try to extract from jets the energy loss ratio, defined in the following way. You have a final measurable jet energy and you divide it by the vacuum energy. And this is subtle and slightly controversial because the vacuum energy of the jet, had there been no medium, is not a priori necessarily well defined. But the reason one can do this is precisely because there is this high energy evolution, high virtuality evolution that is dominated by vacuum-like physics. This presence of a vacuum-like shower inside the medium is well motivated from a theoretical point of view, based not only in the separation of scales between high virtuality and the Q hat of the medium, but also because on formation time arguments. So if you have a vacuum shower that you say you have a shower in the medium that there are some scales for which it's completely dominated by vacuum-like physics, and then at some point the interferences with the medium should occur or the medium should dominate. That point at which the medium scale becomes important would be represented by these dotted lines. However, if you and then from this structure, you will have medium-induced emissions that will typically lead to energy loss and radiation outside of the medium in one form or another. The important thing is that the initial energy, or what we call the vacuum energy, is inside a wide enough R, is well defined, is to a very large extent, it's already defined by the vacuum structure that has already been developed before the medium effects kick in. This is not exact. This is a good approximation, because you could have some very rare kick here at this early stage that could completely modify the virtuality of your jet. However, that's not likely, but that should be further studied. In many models, that possibility is ignored. However, in other models like Joule, that can certainly happen. And one should try to generalize this concept also to models like Joule. Right. So just in the same way that before my battery dies, that's the most important part of the whole thing. Just in the same way that we assume that the high Q square process, for instance, that generates a photon and a quark, is decoupled from the medium because it has a high Q square, then if these splittings have also high enough Q square, they also decouple from the medium in the sense that they do happen inside the medium and are not affected by the medium. So what I'm proposing here is to bring the notion of factorization of the hard scattering just to even a lower Q scales. In this way, of course, we all agree that the energy of the initial parton inside the medium is well defined. right? Just to have a photon of 50 GeV, an initial parton of more or less 50 GeV. Then it will start radiating. So what I'm proposing here is to bring that notion a bit down. If there are some scales that are defined by the vacuum inside the medium, for a widening of R given to the structure of jet collimation, the rest of the structure of the vacuum shower would have happened mostly inside of that radius, and therefore the energy inside that radius is well defined, even in the presence of the medium. This can be applied to several models. In here, I will use mostly the hybrid model, which has a simplified medium response that we are working now on improving. Okay, still 8%. That's amazing. It's like everything I said didn't count. Here we want to pre-process the data not to obtain any biases in the way that the algorithm tries to minimize the loss. If you have steeply falling spectrum, since we want to cover a wide PT range, we want to have a distribution that is as flat as possible in the jet PT, not to give any preference to any specific PT. When we try to extract this energy loss ratio, we also want to have a distribution that is as flat as possible in the energy loss ratio, not to give any preference to any particular energy loss ratio when minimizing the loss. So we use effective sample numbers to obtain flat distributions both in PT and chi at the same time. The network architecture, we use a CNN, well suited for image recognition, with a final convolutional layer to output the energy loss, a fully connected layer to output the energy loss, a number of patches to reduce the possibility of overfitting. And we also have, in not only the CNN, we also tried a simply fully connected neural network where the arguments are physically motivated observables, mainly as checks of the results of the CNN for interpretability. Here is what the jet image in the hybrid model looks like. You have the least quench guys and the most quench guys. They have been rotated such that the groom radius, if found, is at phi equal minus pi halves. You see the basic features of energy loss per jet, which are like an excess of soft particles at large angles. This is a slice for different values of chi. So this is more or less what the machine will be finding. Of course, we won't give it average values. We would give event by event values, event by event, jet by jet images. The prediction performance is pretty good. Here you can see in red the average and the standard deviation, and we perform some sanity checks. For instance, the prediction performance is similar for quark and gluon initiated jets, and most importantly, the network predicts that for vacuum jets, the chi is very close to 1, and we have trained this only on medium jets. But of course, in a sample of medium jets, you get jets that are very modified, jets that are not modified. So the machine correctly predicts that vacuum jets are in fact not modified. This is other setups that are not necessarily relevant right now. What is more relevant is the fact that the performance has a lot of sensitivity on the soft and large angle radiation. So if you remove the soft particles, you will reduce performance a lot. For instance, you can look at the groomed jet image, or you can look at the jet image with particles above 1 GeV or 2 GeV, and the loss increases considerably. So, of course, this has the challenge that there's a large fluctuating background, and that it can be sensitive to hadronization modeling or soft physics in general. So in this model, the fact that most of the physics lies in the soft particles is more a feature than a bug, because there's a essentially, the mechanism of energy loss consists in isodynamization of the high energy modes without any stimulated perturbative splittings. So we should look in other models that admit this definition of chi to see the sensitivity to soft stuff and to see how important it actually is. So you can try to do interpretability. You can try to beat the machine. If the soft particles are so important, well, we can compute the hard ratio, which is the relative contribution of hard particles to the total momentum of the jet. It has a strong correlation with the true chi. However, it's less predictive than the CNN because due to the small slope, correspondence is less linear. But we do get where part of the success of the machine comes from. If we use a selected jet observables like the fermentation functions, longitudinal energy distribution, or the jet shape, this is the angular distribution of the transverse energy inside a jet, we can see that the jet shape outperforms the fermentation function, meaning that the angular distribution is pretty important where those soft particles are. And this motivates the construction of a fit using simply the jet shape, the event by event jet shape. It's a 17 parameter fit, and it's much better than the hard ratio, but still worse than the CNN. However, much of the information that the machine is using from the jet image is contained in the jet shape, in the angular distribution of the particles, especially on the soft ones. So we can try to do some applications with this. We can try to study jets that belong to different quenching classes. If you look at the chi, at the energy loss distribution of jets that are above 200 GeV, you will see that they are very biased towards having small energy loss. Otherwise, they wouldn't have passed the cut. If you instead make the selection in terms of the initial energy estimated through the final energy divided by the energy loss ratio, you recover more like the true actual energy loss distribution of all jets, more akin to having a photon jet sample. However, this is done on inclusive jets, and this method here does not select jets based on whether they lost little or less energy. It only selects jets based on the initial or vacuum, the would-be vacuum energy. So in this way, if you perform cuts on the energy loss ratio, the average of this selection here will represent much more quench jets than the other one. So we distinguish these two: final energy selection, which is what we usually do in experiments and in models, or the initial energy selection that you could do either by looking under the hood of the model, trying to do boson jet, or trying to extract it with machine learning or some kind of specific fit. Now, let's look at some of the interesting observables, like the number of subdrop splittings. In the final energy selection, no matter if you do quench class or unquenched class, both of them are pretty concentrated around no modification. And then this is what you see. The quench class is almost the same as the unquenched class. And in the inclusive, of course, only features things that are akin to having unquenched stuff. So we know that what we are actually seeing is unquenched stuff. We're seeing vacuum-like features. And these features are a reduction in the number of substrate splittings. Guys that split it a lot get more quench and they don't pass the cuts. If instead we use the initial energy selection, you see that the unquenched class is, of course, guys that have less splittings, otherwise they wouldn't belong to the unquenched class. But the quenched class, it now features many of jets that have a chi of 0.5, 0.6, considerable energy loss. And in here, you start seeing like this excess in the number of substrate splittings. For the ground radius, it's a similar story. If you do final energy selection, the inclusive sample coincides with the unquenched sample, which means that what you're measuring is unquenched properties. However, in the initial energy selection, the quenched class will now feature this bump due to medium-induced radiation or soft particles due to medium response that was shown by the Monte Carlo studies I showed before.
Yes.
So this is for the ground radius. If you look at the ZG, the momentum sharing fraction, then you don't see much for the final energy selection, which means that the scale of the emission of the Sudakov is actually not strongly dependent on the splitting fraction, which means that the momentum sharing fraction of that first splitting, it does not actually determine the phase space, the resulting phase space in the jet, and therefore it does not determine energy loss. That's why the inclusive or the quench or all of them, they are consistent with no modification here. In the initial energy selection, when you start looking at jets that actually experience considerable energy loss, you will see an enhancement of the soft ZG. You will see an enhancement of soft subjets precisely at this location, right? This is the angle of that guy, wide angle, soft stuff enhanced. You can also look at the ungroomed observables like the jet shape and the jet fragmentation function, repeat this story. And of course, once you select jets based on their initial energy, not on the final measured energy, then you will see jets that have been much more modified, more enhancement at large R, more enhancement also at soft R, and more of a destruction of the center of the jet also. Another thing that we can do with the energy loss ratio is some kind of tomography applications or setting the base for future tomography applications. We try to extract the length directly, but this has proven a very challenging task. For a given range in chi, you have a relatively wide distribution in L. So given that it's less likely that if you get a good performance on the chi, you get a good performance on the L. But I'm sure, like in Joule, this length has been well defined, also energy weighted, and I think one could try to extract this length in Joule. Is something the definition of chi, which could be controversial for Joule or could be not exactly well defined for Joule because of the random seeds, minor details. In any case, if you select jets with energy loss, have traversed. For instance, you can try to see which is the creation point distribution of the jets that you measure compared to the underlying distribution obtained using Glauber, with the underlying distribution used to generate them, their actual distribution. If you do final energy selection, it means the usual method, you see that you have an excess of jets at the periphery, surface bias, okay. If you do initial energy selection, you see that you're actually measuring all the jets, not only those that lost the least energy, and therefore the creation point distribution coincides precisely with the underlying one, meaning there's no bias in the lengths explored by your jets. There's no bias on the surface. This also applies to the initial jet anisotropies, to V2. The intuitive origin of high PT jet anisotropies, they are precisely a selection bias. For instance, jets that have small chi, a large energy loss, they're more likely to go towards the long path length, and therefore in the usual convention, their V2 is more than 0, and vice versa for large chi. So why you get a V2 greater than 0? Because you don't tend to see so many, because the jets that go over a negative V2, they tend to be more suppressed, simply. So it's essentially a selection bias. If you use initial energy selection, this is V2 versus centrality of the hybrid model using the final energy selection, the one you can compare to experiments. And this is the one that you recover from the initial energy selection, using either the true or the predicted label. It's not perfect, but pretty consistent. And you see that the V2 is 0. By construction, in our model, there's no preferred direction of the jets when they are produced. We have no mechanism to produce any kind of anisotropy. And of course, at high PT, it is the current known mechanism for initial state correlations do not show much of a signal. Also in AA, due to combinatorial effects, many of the color domains would die off. But in any case, one wonders which would be the result in experiments. Is there any underlying V2 of high PT jets, or perhaps not so high PT? We could go even further down. Is there some remaining V2 that is not associated to final state effects and perhaps could give us a clue about the high PT V2 in small systems like PLED? If you select jets based on their chi, based on their energy loss ratio, you will select jets that, if they are unquenched, they are more peripheral. As they are more quenched, they tend to go towards the center. And if you select very, very quenched jets, they will try to be produced less centered than this class here. However, they would be pointing inwards because they want to traverse more length. So you can really gain a new layer of precision for the production point using chi. If you combine your knowledge about in plane or out of plane, which is relatively easily measured as far as I know in experiments, and the knowledge of chi, you can get a good handle on the production point. For instance, you look at in plane guys, if they are little quenched, they will try to be produced the right side, moving right. If they are very quenched, they will be produced at the left side, but moving right, because they will want to traverse more length. So their production point swaps based on the value of chi. And if you know in plane, out of plane, then you know even more. Again, this is akin to having a photon jet selection. However, it has some advantages, such as the fact that one even factors out the fluctuations due to vacuum-like radiation, because we define energy loss with respect to the vacuum-like would-be jet, not with respect to the initial parton, which is the proxy, for which the photon is the proxy. Should I finish? Almost. So this is the most important logic that I try to present here. If there's the presence of a high virtuality early time vacuum-like shower, on one hand, this produces some vacuum set scales that are felt by the medium or resolved by the medium, which determine the total jet quenching to a large extent. Wider jets lose more energy than narrow jets. Therefore, there's a selection bias towards narrow jets. This same assumption at the top here means that there are vacuum set scales that are defined in the medium. And this, for a wide enough R, defines the energy within the cone had there been no medium due to the collimated structure of jets. Therefore, the energy loss ratio is well defined and can be extracted jet by jet. as a counter argument, if the medium scales, if the temperature of the medium was crazy high, as high as the early virtuality, then the early vacuum splittings, they would interfere or completely be replaced by the dynamics of the medium. There would be no selection bias, and there would be no energy loss ratio for any R to define. However, reasonable estimates and phenomenology indicate that this is not the case, or that this case would only be for very small R. And yeah, here's now a summary of the conclusions. We performed an extraction of energy loss jet by jet in the Abri model, obtained good performance. This procedure is generalizable to many models. The angular distribution of soft particles is the most discriminative in this model. Is it in other models? We should check. Important to note that the effect of the local background flow will modify the medium response, will modify the distribution of the hadrons from the wake, because they are sensitive to the local flow. If there's a lot of flow, if the wake did have a lot of time to evolve, this is something that will improve the tomography even more, and that is not yet covered by the simple, although analytical expression that I use so far in this work. And the applications include the study of observables depending on the energy loss ratio. So we can present them in terms of the initial rather than the final energy, and we can mitigate selection bias. And the length and energy loss, even though we cannot extract the length directly yet, it does serve for tomography applications in which we can recover the underlying path lengths and azimuthal anisotropies. Of course, one of the greatest challenges to extract chi in a realistic environment. So we embedded this framework into the jet toy heavy ion with constituent subtraction method, and the performance was greatly reduced. So in a realistic heavy ion environment with a thermal large fluctuating background, after performing background subtraction, this performance is reduced. So this is clearly the greatest challenge in terms of experiments. It does not render the results useless. However, the performance is quite reduced. And one should find ways to perhaps to extract this degree of modification in ways that do not rely so directly on the soft particles, if that's possible in this model or in others. And can we extract the traverse length directly? And can we perform these ratios where also the denominator is matched to the corresponding quenching class? This means that if you want to see jets that are not modified, if you want to see a ratio of 1, nuclear modification of 1, because they are jets that traverse very little length, for instance, then you should divide by the jets that were very little modified. You should divide by a sample of PP jets that would actually lead to those kind of jets. These would require unfolding not only the jet energy, but other properties, other measures such like energy flow correlators or some other things that are not necessarily the energy loss ratio. If we want to achieve that, like purely one nuclear modification factor. But this is, of course, something for the future. And thanks a lot for your patience. And that's all. Thank you for the attention.
Okay, thank you so much, Jamie, for the interesting talk. Do we have questions?
Yeah, 3% amount of
3%. Nice.
Yeah, I have a question that might be quick.
Yeah, go ahead. Yeah, I think we just, yeah.
So did you try with the embedding of the jet images, did you try just the regular network that you used as a validation? Did you try that on the embedded sample, or was it just done with the CNN? Because maybe they might have less performance in both, but maybe it's more generalizable or something like this.
So I don't know if I understood, sorry. You're saying that whether we embed the image, whether we validated the subtraction procedure itself, right?
So I was just saying that you use a CNN, and then there's also this network done to basically like, done as a cross-check that has worse performance. Did you try that on an embedded sample?
Sorry, I did not understand. Can you please repeat?
Yeah, maybe Laura, you can answer because you're closer to the mic, but
So I think what you're trying to ask is whether you tried the other network
yeah,
The fully connected.
Oh,
yeah. So you
whether,
on the embedded, case.
on an embedded
the,
sample.
the
Yeah,
case embedded in
exactly.
the background. If you
the one
tried
that
this
does not
one
rely
it.
on the image.
Yeah,
Mm,
yeah, yeah,
No,
yeah.
I don't think we did. No, no. Yeah. However, yeah. So we were taking the assumption that the jet image contains all of this information, and therefore the jet image will always beat the fully connected network. However, that could not necessarily be the case after embedding and subtracting. You're right.
Okay, thanks. Yeah,
yeah.
I was just curious.
Yeah, thanks.
Danny, that last table that you showed in the background, I have a question there. Do you understand why the 2 GeV cut is worse than the 1 GeV cut?
Yeah, because many medium response particles, they are all below 2 GeV, and there are many between 1 and 2 GeV. So removing the 2 GeV, everything below 2 GeV, is essentially like removing the wake, removing all the particles that have been generated due to medium energy loss. So you're only seeing the effects that remain on the leading particles. And in this model, the leading particles have not suffered any actual perturbative splittings. They have been transferring modes to the hydro. That's the prescription of this model. That's the assumption of this model. So I would be very eager to look into other models that have perturbative splittings to see whether this is still the case, whether all the relevant information is actually contained in the softest particle, or there are some still most splittings they don't tend to modify the leading particle in an extreme way. However, particles of 5-6 GeV that suffer some splittings, there could be some memory before hydrodynamization there because of the slower rate of energy loss in a perturbative scheme that perhaps could be helpful in this scenario where information is above the medium scale. Yeah.
Okay.
Does that answer? Okay. Sorry, perhaps I got.
Yeah, no, I understand.
Yeah. Thank you.
Yeah, thanks.
So if
Yes, go ahead.
now I was going to say that since we did this work, I mean, the most important resistance that I have found, and of course it's the most important point, is whether an energy loss ratio can be defined at all.
Yeah.
Whether but that's why I try to emphasize this logic here, and that's why I try to emphasize the existence of theory supporting this picture here. And I think so. I'm not sure if among you there's people that would like to discuss about this further, but I think this is one of the most important points, and and it would be very interesting to see the extent to which this is true in every model, at least to the extent that it can be checked. For instance, like Jubal, right? You know Jubal Raghav, right? Very well. Perhaps other.
I was going to answer to that, but I didn't want to jump in. So Yeah, so you don't have, obviously, because you mentioned it's a probabilistic thing, right? So we don't have quote unquote unquenched jet for the same quenched jet. But you do have in this, what we did in GSI, there's a way in which you can get the same, parton in vacuum and in the medium, right? So you can only match the parton. The shower is probabilistically different, right? So you can get like a parton level comparison, which is sort of the same as doing a boson jet in that sense. But yeah, I mean, that's what it is.
But like, as far as I understand, like Joule, it does, it can update the shower depending on the on whether the collisions with the medium modify the virtuality of the object, right? Of the propagating object. So
by construction, it's KT ordered, right? So virtuality has to drop.
Right, but as far as I understand, like the first splitting in Joule, it is kind of decided or proposed before medium effects appear, right? And then the first splitting of all, and then you collide with a medium with an elastic collision that modifies the object.
Correct.
However, it will not necessarily modify the splitting or the virtuality of the splitting. It will have this decision whether the formation time has actually been reduced or not, right? Which is like some kind of implementation of the LPM effect. So I wonder if those splittings that are proposed but are actually not modified in the end, then would those be like the vacuum-like jet, that
I see what you're saying. Yeah. So this is something that you can actually see in Liliana's latest paper, Liliana and Corina.
Oh, okay. I didn't know they were focusing on that.
Yeah. So they select on the formation time of the split at the parton level and the first split, and then you can show that the effect of the medium, and it's mostly vacuum-like in that case. So they're exactly the way you're saying.
So there's some hope that we can try to do something similar in Joule as well. Yeah, that's
sure. Yes.
Great. Yeah, thanks for pointing that article to me.
Yeah.
So I guess I'll ask like a more big picture question. So like when do you think, or how feasible do you think this would be, like applying to data? Like what needs to be done in order for this to be something that we could do in data? Because of course I think we're all interested in doing something like this in data, where we can we could try to do it with doing a gluon tag jet or whatever, but doing those are going to be less quenching effects. So trying to access the more quenched jets in data is something we all, I think, are excited to do.
Yeah, so clearly, photon jet is the most natural way to do that, clearly, right? Because you select on an object that has been, then if you put the PT of the jet much below the PT of the triggered object, like the Z or the gamma, then you will get a much larger amount of quenched jets. That's the most natural way. But if you want to use this, then first I think we should bring in more models, and we should see which of these conclusions are generalizable. If you train in one model, will you actually be able to have a reasonable performance in another model? This should be more or less the case to the extent that they can reproduce the same sort of data, perhaps. If their phenomenology is similar, you should expect that some of these features are similar. So yeah, bringing in more models and not necessarily use this energy loss ratio, although I find it really convenient and well motivated, but there could be other choices. But if you have some strong support from different models, from the most commonly used models, and then you are able to overcome the background subtraction, in which perhaps you were mentioning, you could try other methods, of course, than the ones we've tried here, or you could even do the machine learning subtraction itself to subtract the background, such that, did we ever try that, like trying to extract the energy loss ratio on the raw sample, on the embedded sample, without doing any constituent subtraction method or anything? I don't think if we tried. But perhaps combining background subtraction, machine learning with this other stage of extracting the energy loss ratio, provided you have generalizability of models and deal with the background subtraction, I think there should be a nice way, a nice road to try this in data, I think. So yeah, perhaps, yeah, we could organize some kind of dedicated workshop or something. Hopefully in person, because because online, I don't think it's so cool. Yeah.
No, I think
Yeah.
that would be really cool.
A follow-up on what you were just saying, because you can also look at variations within a model and see how robust the answer is, correct? Like you can use the same model that has a dial and then turn the dial and then see how generalizable
Yeah.
prediction is. Has this been done?
Yeah, that's a good suggestion. So we also tried this within the context of this hybrid model. We tried different energy loss rates, like one that is inspired on collisional energy loss, one that is inspired on radiative energy loss, that have the appropriate characteristic length and energy dependencies, without any actual induced splittings, right? So what you're saying, like taking a model and changing parts of it, and the prediction performance is pretty consistent. Of course, yeah, this is encouraging. However, it's not the solid proof that one wants, because even though we dial different energy loss path length dependencies, the main info is still contained on the hadrons that come from the medium response, from the wake, which is essentially having a bit more QGP in a certain direction, and that decays into soft hadron. So this is, I'm afraid, perhaps the thing that the machine is learning the most, and I would like to see how it happens in other models in which energy loss happens more gradually, like more successive splittings before all memory is lost and before hydrodynamization is reached. And I would like to see if in these models there's another difference or not. But yeah, we have tried dialing. Yes, that was a good idea.
Nice. Thanks.
Thanks to you.
Any other questions? I didn't see any. I'm using the wrong mouse. Okay, cool. Well, if we have no other questions, let's thank you.
Yeah.